This conference will now be recorded.
Hi, good morning, everyone. Hope you're able to hear me very well as see my screen. One of you, please
Yes.
confirm. Okay,
Yes,
that's
Madam.
great. Good morning. So let's get going then. So hope all of you are in front of computers. So we started with our toy project, uh, and I want each one of you to try out whatever we are writing as some code in Python to kind of understand some uh, or build intuition about model complexity. That's why we are doing this toy project. So hope all of you are sitting in front of your computers. I will go slow so that all of you take your time and type whatever I'm showing there. And in case you want me to stop for a while, please let me know. I'll stop. If you want me to go back to a previous slide, please tell me. I will do that. So the whole idea is that using this toy project, let us build a good intuition into what is this whole model building process and what is this whole concept about model complexity, and understand it so that when we do the next three projects with real data sets and solve some real machine learning problems, one in regression analysis, another in classification building, and also in the third, a cluster analysis, you will understand what we have done, why we have done. So that is why we will go slow, and you have a right to stop me anytime. Okay. And also, please feel free to ask me questions whenever you have them. So don't hesitate. Okay. So this is our second session on our toy project, and this is actually our 16th online session on our machine learning foundations course. So good that we are able to continue uninterrupted, and I am very happy that a lot of you are showing a lot of interest and hope the real learning is taking place. Actually, that is the goal of this whole course. So again, recapping what we have done in the previous session is that we built our own synthetic data set. Another word for synthetic is artificial data set. So what we did, we created one column input feature, only one input feature, X. How did we create that? We generally created using our np dot random function, and we used linear space, linspace function, and we created values starting from 0 ending at 2 pi, that is something around 6.14, and we have done linearly spaced 100 values, and we created an array, numpy array of 100 values. We called them X. Then what we did, we also pulled from a normal distribution, statistical distribution, a data. And how did we pull that? We used np.random.normal function, and we pulled 100 numbers which have 0 mean and zero point 0.5 standard deviation. And because we put a particular random seed, we get consistent kind of that numbers, and we called them noise. Then we created a target variable y by using this x and noise. So what we did is that we have made a function y equal to sin x plus that noise, and we created another array of 100 numbers y. Then we put x as input feature and y as a target variable into a pandas data frame, and we saved it to a CSV in the last session. So we have created our own synthetic data set. So the true underlying relationship between the input feature x and the target variable y, we knew because that is y equal to sin x, plus actually we added a noise to make it much more real, and we distorted it a little bit by adding that noise. Now our goal is to somehow build, using this data, train some models and build some models and capture the true underlying relationship. Okay, so create or select a model which is not underfit, at the same time it's not overfit. We wanted to kind of select a winning model which is actually a right fit. So to be able to do that, we have to build many models with different kinds of complexity. That's what we will do now in the next few lessons. So hope you're all there with me with respect to where we ended last session, and you have saved your the numbers into a CSV. Okay, so we will get into our coding section soon, but let me bring a little bit of concept, then we'll move to coding section. So we will, in this lesson, we'll start building models. So we'll start on the extremely simple end of models to illustrate their key limitations today. Okay, we will slowly build the complexity and demonstrate to you what is this whole idea of model complexity. Okay, so we will start with a very simple model, and this model actually doesn't need an algorithm also. Just whatever my x and y are there. Now right now I have x and y. Okay, then I will use this mathematical expression y hat, that is my predicted y. I want to build using y mean. So whatever values are there, 100 values of y, I add all of them. I have 100 values of x and 100 values of y. I will add all of them and I calculate a mean. I'll use it as y bar or y mean. So I put that value, whatever is that value, let's say that is some 0.1. So I put 0.1 everywhere. So that is my predicted variable. No matter what is my x, my model tells your y is predicted y is 0.1. So that is kind of model, because we are using mean y bar as our predictor. So we are actually calling it as mean model. Okay, so let us look at it. So our basically y bar is nothing but average of all y's in the data set, and y hat is my predicted variable. This is the simplest model. No matter what is there, my xy relationship, I am ignoring all that relationship. I am telling for whatever new value of x, my prediction will be y bar. Okay, that is average of all y's. Like for example, we have scores of Virat Kohli over a period of last 200 one-day internationals, and his average in one day is 80 runs. So in the future matches, no matter what, we tell that he is going to hit 80. Means we are taking average and telling that that is my prediction. That is as simple as that. Hope you are clear. Okay, so let us move on. So if we put that and overlay that uh, model. So here the blue dots are our scatter plots, and the black dotted line is actually my model. Okay, so what I have done, I calculated my average of all y's, that is actually minus 0.0172. Okay, and I am putting for all x, x actually is my 100 values. Okay, and y hat is my 100 values of 0.01. I will plot 0.017. I put all of them and draw. Any such line will be a horizontal line cutting across your data. Okay, at a mean point. So this is my black dotted line is my model. So using this model, I will try to predict for any other new x. Let us say I predict for some x which is close to 1. Okay, so my actual value is this blue dot here, and my based on this black dotted line also, that also will be same. So it is accurate. But if you look at it here, these points, the error will be very, very high. So for 5, if I want to predict using my model tells it is minus 0.017, whereas somewhere here, this is the actual thing. Anyway, we know sin x, so somewhere it is falling here. So there is a huge error between that. So that is the performance of mean model. So we will do all this by coding it. Okay. So we basically, a mean model, we are not allowing our model, through our model, any flexibility for the model to learn the data. We are actually, it is not having any flexibility other than drawing a horizontal line across the mean. Okay, so it has its own issues. Okay, so basically, in summary, our mean model is an example of an underfit to the data. It is not complex enough because we did not give it enough flexibility. So based on that inherent capability, it is creating a model, and that's what is the accuracy of that. Okay, let us say we want to increase and give more flexibility through an algorithm, and let's call it as linear regression algorithm. Okay, so we use a mathematical function like y hat, my predicted y, equal to beta 0 plus beta 1 x. By allowing this flexibility using a linear regression algorithm, if I learn this data that is on my scatter plot between x and y, I am allowing it more flexibility. So it actually learns this data and it searches through this data space throughout and stops and finds the best fit line that actually cuts across this data. Because I am giving y hat equal to beta 0 plus beta 1 x, by nature, this can only represent slanted straight lines. So when I give y hat equal to beta 0 plus beta 1 x and use a scikit learning algorithm, linear regression algorithm, and train that algorithm using my data, it actually fits the data into this red dotted line. So using this algorithm, this red dotted line is my model. Okay, so basically what it does, once we run the algorithm, it searches through this space, it fits many lines, and it stops at a place where the sum of squared distances or sum of squared errors is minimum. What is really sum of squared errors? So there is a x in our table, there is a y in our table, and there is this y hat that is calculated. Okay, so there are 100 values here, 100x. Okay, now for every x, so basically by the end of this fitting process, the regression algorithm will throw out two values. It will throw a value for beta 0 and it will throw a value for beta 1. Okay, let's say this is x1 and x2 values. Okay, so now what it does, actually for every line, it actually substitutes x in here and substitutes beta 0 value here and substitutes beta 1 value here and calculates y hat and populates 100 values. Okay, for wherever, whichever this red dotted line, if you look at sigma of I equal to 1 to n, this is 1 to 100 for us, yi minus yi hat squared. If you look at this value for this thing, for this red dotted line, that will be the minimum. Okay, so that is what the linear regression algorithm will optimize after reading the data that we give it to that algorithm. It searches through the space, many lines are possible, but it will stop at a line which is where this value is the minimum, and it will throughout. Hey, I fitted your model using a slanted straight line, and for the best fit line, this is the beta 0 and this is the beta 1. Any questions so far? Shall I move on?
Yes, sir.
Okay, so now when I have this model, I can also use this for prediction. Let's say I want to predict, let's say for 3.5, what is my predicted y? Then I will start at x and go back, go up to this red line and draw it to here. Okay, so it is somewhere close to 0. Okay, sine whatever 90 kind of thing, close to 0. So here this model, again, if you look at from this model, is it able to capture the true underlying relationship between my input feature and the
Madhu, we lost you. We cannot hear you.
sorry, I think you lost me for a while. So I'm asking a question now based on what you are seeing, this linear regression based model, is it a good fit for this data?
No, sir. It is again underfit.
It is an underfit. It is little better than our the mean kind of model, too simplistic model. This at least is capturing the slope that is happening in the data. Okay, so at least it is capturing that slope, but the amount of flexibility we gave is only using this mathematical mapping function. No matter how much data you give it to this, okay, it will only represent, or it will learn the data and put a model that only can be represented using a slanted straight line. It cannot understand the curvy relationship as long as we make it a very simple linear regression. Maybe we have to increase the complexity and add some polynomial terms to actually give it to a flexibility to understand the curvy relationship. But right now we are not allowing it. So we allowed flexibility to understand only the straight slanted lines. So that is the model complexity we gave. But again, seeing the graph, I can tell it is an underfit. But typically in our real projects, it is not going to be as simple as that. I will have my x input feature will be x1, x2, x3, x4, x5, like x20. Then my y will be there. So 20 features columns, input features, and one y. So then a linear regression, what will be your typical linear regression equation? Y hat equal to beta 0 plus beta 1 x1 beta 2 x2 plus beta 3 x3 plus go on till beta 20 x20. So this is again a regression, linear regression, but this is a simple linear regression because one x only is there. But here more x's are there, more features are there. These are called multiple linear regression. Okay, typically all our problems we solve will be not having one input feature. They will have at least 100 input features. Okay, so when we really use a simple linear regression, means we will be using multiple linear regression. Keep that in mind. That cannot be plotted in a xy plot. It will be much more multidimensional. You have to imagine that whole picture as a horizontal plane in your room in front of you, and in that horizontal plane lot of points are there, and cutting across the point there is a surface which actually is the best surface that cuts across the data. Imagining, visualizing is very tough. So how do I know whether that is a good model or not? So usually we don't use this visualization to tell a model is good model or bad model? We use something called empirical evaluation. After we build models, we test it using a lot of data, calculate some metrics. Okay, empirical analysis we do using a lot of metrics, and then we select a winner. But we'll come to that. Keep that in mind. So far is clear. Shall I move forward?
Yes, sir.
Okay. So the limitation of this linearity is that it can only understand the slants using straight lines in your data. Okay, because we are allowing it to learn only using this simple mathematical function, that is y hat equal to beta 0 plus beta 1x. Because we are not allowing it that flexibility, because the model is not complex enough, it cannot capture these curvy relationships in the data. That is the problem with linearity. Okay, so we have to increase the complexity of uh, the algorithm, and thus enable more flexibility for the algorithm to learn from data in case it has to understand some curvy relationship in the data. Okay, keep that in mind. So in summary, our linear regression model is still not complex or flexible enough to kind of make predictive accurate predictions. Clear? So now in this today's lesson, we'll only build up to this linear regression model. Then in day after tomorrow's lesson, we will start letting it get more flexibility, or we'll make it more complex and see, we'll give it extreme complex and see how this whole model complexity issue evolves. Okay, so now let us get hands-on practice with the concept. So all of you start. Hope you are in front of your Jupyter notebooks all opened. So let us do that. So first thing is that you always keep this as a header, and these headers will increase as we move forward. So import numpy as np, import pandas as pd, because these all libraries will be using it, and then some visualization libraries. So from matplotlib, import pyplot as plt, because we'll be using this plt, pd, np, and also import seaborn as SNS. And if we want to see a particular style graphs, just put this SNS dot set underscore style, pass a string dark grid. So already you have done that. Just copy paste onto your today's IPYNB file and run it. Okay, so once you are ready, let me know. Are you ready? Can I?
Yes, sir.
Yeah. Okay, so we are ready with the importing all libraries. So what we will do, we'll build a mean model first. For this, no need of an algorithm also. Okay, what is that mathematical expression? It is y hat equal to y bar. Okay, we can write our own code to this. It's not a issue. So the above equation simply means our model will always predict the value of y for any new observation to be the average of our previous values of y, regardless of the value of x. Okay, so that is the mean model we are going to build and plot. So now read your whatever you saved last time of this table that we created of x and y. Okay, just read it back into df. Give a variable name df. Whatever you can give, but I'm giving df. And what pd function we use? Pd dot read underscore csv. And if you saved in your whatever working directory with this whatever name last time you saved, just give it in a string argument, the file name, and see the first 5 observations of your table and check whether you are getting the same data that you have saved. Okay, got it?
Yeah.
Okay, so we are now having our data that we created. We can start playing with it now. Okay, so that is there in a variable called df now. Okay, so now let us build our mean model. Mean model is very straightforward. We don't need an algorithm. We don't need to even go to scikit-learn and import it right now. Okay, because it is a very simple thing. So what we have to do, we have to calculate mean of our y column. Okay, so I am calling it as pred variable name, and I am using my np dot mean function. Okay, or you can do df dot y dot mean also, but anyway we are using np dot mean and passing my y column. So the mean value is stored in now my variable pred. If you print pred, the value is coming to minus 0.01725. that is the mean of the y column in our table. Okay, the average value of y in our simulated data set. Okay, so that will be always our prediction. Okay, that is what, as simple as that we are telling. Okay, got it?
Yeah.
Okay, so we'll move on. So but now we want to plot it. To plot it, every time our whatever lib that thing requires, if there are 100 values of x, I have to give 100 values of y, then only it will plot. So right now pred has only one value, so we have to, while plotting on the y-axis, we have to put spread for 100 times. We have to fully populate that column pred or y-axis with 100. Keep that in mind. Right now, because we did, it is a simple one value. Okay, now let us plot. So let us see how the model fits the training data. We will get into formal evaluation metrics later on, because this is a simple problem with only one x and one y. We are able to see clearly on the screen, but that is not how we really do in real projects. In our real projects, we will use formal evaluation metrics to tell whether this model is good or bad. Okay, before we start crunching numbers, it will be much more intuitive to visually evaluate our models. So let us plot. So we have already learnt there is plt dot scatter. Okay, we have to pass df dot x comma df dot y, then it will put a scatter plot of our all xy numbers. Okay, all this like that. Okay, then we will use plt dot plot again, but this time plot the predictions from our mean model as a dotted black line. Okay, so what I want to do is that I want to use plt dot plot, pass my x as x, but y should be 100 values of pred. Okay, that is what I want to do, and I want to plot a black line. Okay, okay, so I want to plot something like this, all 100 values of pred. So x, I have to give df dot x, but y should be my pred. Okay, because it is only one value is there, I will make it as a list and star and 100. Then I will have that list, when is multiplied by 100, you will have repetition of 100 values. So you plot on the x plt dot plot, but on the y you plot this, then you will get that kind of black dotted line. Okay, so one thing to note is that if you are plotting a line plot with plt dot plot function, it expects two arrays of equal length, one array for x and one array for y. So for this black dotted or model line to come, I have to have my predictions, PRED 100 times it has to be there. Then only it will plot like this. Otherwise, it will give error. Okay. So let us do that. So basically, our length of df dot x I'm checking, it is 100. We know that x column has 100, whereas our PRED is having only one. Therefore, in order to plot this chart, we need to create a new list of predicted values of length 100. So we can do so by putting our predicted value into one element list. I'm putting those square brackets and then duplicate it with multiply by length of df dot x, which is nothing but 100. Okay, that's how we will plot them. So now you type this code and see for yourself. So basically what we are doing, we calculated PRED. Now we are putting our scatter plot and we are overlaying our mean model on top of that. Okay, using first one plt dot scatter, these blue dots are drawn. Okay, then for putting my black dotted line, I am using plt dot plot. My x-axis values I'm giving, pick it from df dot x, that column. Y I am telling, I'm here. Actually, you can make it another statement where before that you call some other variable predictions. Okay, if you are little bit careful, this is actually y. So you can do that PRED, which is having minus 0.017. Okay, star length of your df dot x. Okay, that is your y-axis. So instead of putting, I am putting as a y as a calculation in the argument for y. Hope you got it. And I wanted to do it in a little bit different color. So K minus minus will put it in black. Clear? Got it?
Yeah, it's coming.
Okay. So you have
Yes, sir.
built your mean model first. Okay. It is now once we build models, a model is a model, but we have to evaluate how good is it. So we evaluate using some formal metrics. So regression algorithms have some formal metrics. Classification algorithms have some formal metrics. Clustering doesn't have many formal metrics, but some kind of statistical techniques using which we can assess a particular cluster is good or better than other or not. That is possible, but we will learn all of them, don't worry. Okay, so you got it. So now let us evaluate this. So problem is this, does this look like a good model? No, especially these, especially for x values, which is 1 to somewhere 3. Okay, all these are, it is not capturing anything well. Okay, so these observations will always be predicted poorly using a mean model. Okay, so it is a an underfit model, or in other words, if we want to use bias variance, what is that? We chose to use an algorithm or a model that is having high bias and low variance. So that is why we are actually in the as an output we are creating an underfit model, or in other words, we haven't given enough flexibility for my model to learn the data by restricting with some particular mapping function. Clear? Shall I move forward?
Yes, sir.
Okay. Now we will increase complexity. We want to give little bit more flexibility to our model to understand this data that is there, x and y. Okay, so the mean model can only fit horizontal lines. However, a linear regression can fit lines with slopes. So I want to increase the complexity, or in other words, I want to use a little bit uh, different kind of algorithm which is more complex than a mean model. So in other words, a linear regression is actually able to model the relationship between input feature X and target variable Y. We are able to model a change in Y as X changes instead of taking the simple average of Y's. So any change in X, how it is affecting change of Y. For every unit increase of X, how much Y is increasing. If it is increasing in a positive direction, slope is going up. For every increment of X, the Y is getting into negative, then it is slope is falling. Okay, that is the meaning of that. So basically, this is nothing but Y equal to mx plus c kind of equation. So in our terminology, always we will use Y hat equal to beta 0 plus beta 1 x. This is the mapping function we use in a simple linear regression model. So beta 0 and beta 1 are both learned from the data set. So based on the data that I give x and y, it will learn, and for the best fit line, it will tell what is the beta 0 and what is the beta 1. These are called actually model parameters sometimes. But what is beta 0? Beta 0 is we call y-intercept. Okay. And for a simple linear regression, beta 1 is slope. Okay. So beta 0 is actually y-intercept. Like let's say there is a line. Okay. It's going like this. So what is the y value when x equal to 0? That is called your beta 0, y-intercept. And the slope is calculated based on what is the increment of your x, how much this increment is causing the increment in the y. It is a positive number, and if it is like this, it is a positive big number, and if it is like this, negative compared to this negative big number. So that is how it is calculated. There is a statistical way we can calculate for such an equation m. Okay, there is a equation. We'll work out on those things later manually, but that is what we'll be doing. Thus, when you fit a linear regression model, you are really just estimating the best values for beta 0 and beta 1 for your given data. Okay, so your data is read, and the algorithm will run through various lines of various slant slopes and finally stops at a line where the sum of squared distances, that is sigma I equal to 1 to n yi minus yi hat square, is the minimum. For that line it will stop, and for that line it will tell the y-intercept of that line is beta 0 is this number, and the slope of that line beta 1 is this one. So that is what your algorithm will give to you. Okay, so let us do that now by putting the code. So now we have to write very complex logic if we have to really build that kind of algorithm. Complex maths has to be done. Then you have to have some logic, something like gradient descent logic, because if you, many ways it can be written, because it has to search through the space by putting many lines and finally arrive at a particular line with the best beta 0 beta 1 for that data. Means the algorithm has to be cleverly built, and it has to be fast. It cannot be taking enormous amount of time for a large data. So that is why scikit-learn Python library for machine learning already built these algorithms, and we will import that algorithm. We will not develop that algorithm. We will use that algorithm. So to do that, please do this. We have to import from, again, sklearn dot linear underscore model. This is the library, sub library. From there we are importing this class or a model, that is linear regression. Keep noticing the caps. L is caps, R is caps, no space. And again, you have to keep on remembering this sklearn dot linear underscore model. Sometimes classifiers will be there in another library. Then clustering algorithms will be in another library. So we'll keep coming to them. So they've organized within the scikit-learn algorithm library into sublibraries and put various algorithms. Okay. So did you do this?
Yeah, done.
Okay. So if without any problem you are able to do, means you have all the things in place, installation is done. Okay, now we will use this. So what we will do, I'm explaining the code first and then we'll write. Anytime we are using a model, now I've imported already this linear regression, already a class of Python already developed for me. So I am instantiating using a simple word, so that going forward I will use this under rather than the big line. So I'm calling it as LM. You can call anything, but I am doing it as, because it is linear model. Okay. Then all these algorithms, actually most important two functions of all learning algorithms. Okay, there is that two functions are there. One is called dot fit function, and then another function is called dot predict function. Okay, so dot fit always requires, first you have to give as an argument features, means your all x columns. Okay, features, comma, target, y. Okay, or you can give x. Usually they call caps x from a terminology point, and small y, because cap x actually represents multiple x's. Okay, and predict, you want to predict for all features, whatever x values you want to predict, then it will, you can do that. Or if you want to predict for a new value, then you have to pass a two-dimensional array. Let's say I want to predict for what is for 5, what is my output based on this model. So that is how I will pass. So keep noticing this. There is dot fit and dot predict, and also there will be some metrics that will come to later, but these are important. So dot fit requires me to give two arguments, features, comma, target. So I cannot pass my df directly. I have to first separate out from my df features and then target. That is what I will do always. Okay, so what I'm doing here, I'm dropping my y from my df, because it is having now x and y. Right now it has x and y, so I am dropping this by doing this df dot drop, and I am dropping my y column. X is equal to 1 means to full column I am dropping, so the resultant will be x. I am calling it as features. You can call anything, you can call cap x, okay, or call it as features. Okay, then what is target? Target, only the df dot y column, I am equating it to a variable called target. So target, if I look at feature now, x, the series object x will be there. Target will have my panda series object y will be there. So I separated it. Why I separated it? Because my lm dot predict requires these things like that. So then I am using my lm dot fit method. Okay, I am passing my features and target. This is nothing but lm dot fit is nothing but I am using my data to train the model. Okay, so I am passing my data to my algorithm. So when I am passing, it is being trained, or in other words, my algorithm will learn the data. When it learns the data, it does whatever it is supposed to do, and then it computes. At least for this, it will compute beta 0, beta 1, and tells me for your best fit line, these are the coefficients. Okay, so that is what we will do in the code now. So let us write this code. Okay, so let us build a linear model now for our noisy sine wave data set. So I instantiated linear regression algorithm as LM, do that. Then I'm separating out my input features and target variable. Okay, by this is the best way. Many ways it can be done, but this is a very simple, straightforward way, where first drop y, the target variable, and equate it to features. If there are 100 x's and 1 y, so by dropping y, remaining is actually only input features. Put that into features, and then only y, you call it as target. and you have separated it. Now using this lm dot fit and passing features and target, you are telling your linear regression algorithm, hey, here is my data, learn from it. Sometimes this is very simple data, only 100, but the real data when we do, it will be some 150 columns with 1 lakh rows. At that time, this whole fit can take little bit of time because it does a lot of work behind the scenes. Now you may not experience it, but when we build some of these real models for real data sets, then you should have little bit of patience, especially if your machine is 4 GB RAM with so whatever CPUs it has. So anyway, I'm telling right now. So you got this without any errors. So some output it will give. Okay, some fit n underscore jobs is equal to 1. It tells how many CPUs are there, how many CPUs it has used to solve this problem, those kind of things. Don't worry about all these things as long as it doesn't throw errors now. So got it?
Yeah, got it. Yes, honey.
Okay. So now whatever LM object you have, that is your fitted model, because you want to equate it to some my fitted model, you can put my fitted model equal to lm dot fit, then your my fitted model you can analyze. But anyway, we didn't do that, so our lm is now the fitted model. So what we have to do now is that let us look at it for the best fit line. So it has some parameters. While calculating, these are the names with which we can access them. So lm dot intercept, again spelling you have to carefully look at it, and then underscore. Actually this is the for the best fit line for the training that we have done. This is the beta 0 value, 0.82386 is my beta 0 value. Then when I am printing my lm dot coef underscore, this is my beta 1 value, which is returned as my a list. Let us say I have another equation, y hat equal to beta 0 plus beta 1 x1 plus beta 2 x2. This is also a linear regression algorithm. We are giving in our table we have two input features, and for that it will use this kind of thing. And then beta 0 is your intercept, but for beta 1 and beta 2 it will give two values, a list of one value for beta 1, okay, and another value for beta 2. If you have 100 of them, it will give 100 values, 100 coefficients. Clear? Did you get this?
Yes.
Okay.
Madhu,
Now,
Joseph here.
yeah, Joseph.
I'm
Go
getting
on.
an error in the previous. Can you go to the previous slide? It is
This
pulling.
one.
Yes, the
Okay.
y-axis, it was giving some error.
So this is a string y because that is the column name. Okay, and comma axis
Okay.
equal to 1 we are giving, that will be your column, full column will be dropped. See whether you have
Okay.
before this you got everything right, then only some typographical mistake only will be there, nothing beyond that. So just check whether you gave this or not.
Okay, Madhu, you continue. Probably I'll check. Sorry, Amin.
Somebody else?
Yeah, this is Amir. I'm getting error something like fit missing one required positional argument.
Fit. You gave these features and target right spellings. Your typographical mistakes only will cause. Okay, if you have given features as the variable for the x column, that only has to be passed. Now let's say target spelling is wrong, then it will tell missing. So check that.
Madhu, I am getting y not found in axis. That is the error I am getting. Key error.
This you have put a string y in single quotes.
Yes.
Yeah, in single quotes only, lowercase y only I have mentioned.
Okay. So your column name, when you defined your PD data frame, is it same? So you go and see your df.head. What is the column name? Is it caps Y or anything else? See that.
No, all lowercase I, but there also I was getting some error actually. pd.head and all. That is
Okay.
the reason I'm not able to get it.
Okay. Okay. Anyway, as far as I know, only typographical things. Again, if you are from yesterday, you are using something. Okay. So there is an issue with your Jupyter notebooks. You have to run all the cells. Otherwise,
Okay.
it will not work, because that is why you have to go to kernel. If you are extending on the same notebook, okay, PD has been imported earlier, so you have not done that, rerun that cell. Now, for as far as for today's session is concerned, it tells PD is not there. That's why it will give a problem.
Okay.
So you have to run all the cells. If you are kind of appending from where we left yesterday, before starting this, run all of them. Otherwise, you have a problem. Once you run, everything will work actually, because
Okay.
whatever it forgets about yesterday's thing once you came out of that kernel, or you go to the kernel, restart and run all cells, then also it will be over. Okay, shall I move? For some people, at least you got up to here, na?
Yeah,
Yes, sir.
Master.
Okay, so others also will get, just some simple issues only will be there. So anyway, the first value is 0.82. It is the y-intercept beta 0. That is what, for the best fit line, it has calculated. This is where the line crosses the y-axis. So in other words, when you set x equal to 0, this is the predicted value of y. Okay. The second value, minus 0.27, 267, whatever, is the coefficient beta 1. So this is the slope of y in relation to x. In other words, whenever x increases by 1, the predicted value of y will decrease by 0.27, negative slope. So line is dropping like that. Okay, that is the how we understand this. So now let us understand linear regression performance. Okay, so I want to use this whatever model now has been put. Okay, that is the fitted model. We didn't change the name, so LM. So I want to use this dot predict. Okay, so dot predict, I can use this predict for now. I want to use this model to predict y for a particular x value. Let's say, let us look at for 0. Let us first, what do you think will happen when we call lm.predict 0? We want to predict y value for x equal to 0. What will happen? Our equation is y hat equal to beta 0 plus beta 1 x. Okay, x equal to 0. So this term is gone. So y hat equal to beta 0. What is our beta 0 value? Beta 0 is 0.827. So if I make a prediction using my model for 0, then I will get a value for beta 0, that is 0.82. Okay, so only thing is that dot predict function expects a 2D array like element input. So if we want to predict the value for x equal to 0, we actually enclose it as in 2 square brackets. So let us do this and tell me whether you got the answer or not. So here I am using my model to predict y for a value 0. This is how I am using the syntax. If you give like lm dot predict argument 0, it will give error, whereas you have to give like this actually. Tell me whether you got it or not.
Yeah, it is coming same.
Okay, so basically we are using our model to predict for x equal to 0, then anyway we know the answer, so it is beta 1. So your whatever lm dot intercept underscore also same thing. Okay, so it's predicting. Now let us do for lm dot predict for 2. What will happen? X equal to 2, I am my value x equal to 2. I am asking what is my predicted y. This is the question. What it will do? It will do y hat equal to beta 0 plus beta 1 x. So beta 0 I know, beta 1 I know, x I am at 2. Okay, so it substitutes x into this also beta 0 beta 1 and calculates and throws you the answer. That is what it does. Okay, let's do this. So lm dot predict for 2. So x equal to 2. So beta 0 plus beta 0 is my 0.82 something, and then beta 1 is my point minus point something, x is 2. So it calculates the value by substituting all these coefficients and x value. Okay, did you get it?
Yeah.
So the same thing can be calculated like this. You lm dot intercept underscore, that is my beta 0 plus 2 is my x, and beta 1 is my lm dot coefficient underscore. So I'm substituting all the values and calculating manually, not through predict function. I'm doing. So are you getting the same value again?
Yeah. Same value is coming.
Okay, so that is how it happens. It calculates y hat, but then if we want to predict, now I have a table x and y, and I want to, for same x, not unseen x, same x I also want to calculate y hat. If I want to overlay the plot, then what I will do is that I will call this dot predict function and pass my features. Features is having all 100 values of x. Anyway, this is actual y. In my table, it is already there. So now when I do predict and pass features, what happens? For this whole column, this equation is applied, beta 0, beta 1, and that particular x value, and calculation is done. Same thing again, that x value and beta 0, beta 1 substituted, calculates and puts all of them. Then I can use it to put a graph to see what is my model. Okay, let us do that. Okay, so let us overlay the linear regression model and the original data set and evaluate its performance visually. Okay, so same thing we are doing again. So here what we am doing is that plt dot scatter, this scatter plot I am doing. Okay, so df dot x comma df dot y, then plt dot plot again I'm using. On the x-axis I am putting dfx, my x column 100 values. Here I am using my y hat. Here whatever this y hat 100 things I am using for my y, plotting for y-axis. So lm dot predict, passing my features, and I want to put that thing in black thing. So when I plot, this slanted black line is my model based on my linear regression algorithm. Okay, tell me when you got it. Got it?
Yes, Madhu.
Okay, so this is our linear regression algorithm. We have earlier built mean model, so you can see this is much more different. This is not a horizontal line across the mean, but it is for this data the best fit slanted line with the beta 0 beta 1. We got it. Now we can use this for prediction. This is little better than, so how this model, how did this model do? Well, it's pretty obvious that this linear model fits the pattern of the data better than the mean model. We know that by seeing it. Okay, by allowing the line to have a slope, you have permitted more flexibility. than the simple horizontal line of our mean model. But we are also seeing a limitation of the linear model, that is assumption of linearity. No matter how much data I give it, it will not do any curvy kind of relationships, it will not capture. So linear regression actually assumes that the target variable has a linear relationship with the input features. Y hat equal to beta 0 plus beta 1x. That is the thing that is limited with that. So therefore, we cannot capture curvy relationships like our sine waves. Okay, they cannot be represented using this simple linear regression model. So in summary, our linear regression model is still not complex or flexible enough. So it is still an underfit model that we have done. So now still we are not able to capture the true underlying relationship. Maybe we have to crank up the complexity and build more models with more computational models to really capture the true underlying relationship very accurately. Okay, that exercise will continue now, but for today, you have any questions, let me know. Otherwise, what I will do is that I will just go back. Okay, and okay, so whatever, some people could not do the code thing. So again, I am doing, for every exercise, I am putting a separate IPYNB file and running from the beginning. Okay, if you are appending it, okay, be careful. So there is a kernel here. We can restart and clear output. If you have already run all of them, you want to clear the output because I am not able to go through the code properly. You can use this or restart and run all. Lot of code cells are there. You want to run all of them from top to down. You can do that. Then you can append very easily. Otherwise, it will lose whatever the context once the kernel is stopped. So anyway, here this is the header for us importing all the things. Okay, so everything is in place now after executing that cell. So we saved the simulated underscore data dot csv. So I am again reading it back. So the same data is there, x column, y column, and this is how we have saved it. Okay, you can see tail also if you want, but it's a pandas data frame that we saved, it is there. Now here I wanted to build a simple mean model. I don't need an algorithm, just I can use np.mean function on my df.y and store that value in a variable called pred. Okay, and pred is calculated as minus 0.017, so it is done. Okay, now only thing is that if I want to plot this, I need 100 values of pred, otherwise I cannot plot it. So here we are seeing x has 100 values, I'm just telling that, and then length of df.x is 100. So if you want to really do the plot xy chart, then both x and y have to have equal number of kind of elements in that arrays. So x has 100, but pred is having only 1. Okay, if you look at it, pred has just 1, it is not an array also. So we know if I can convert it as a list object and multiply by 5, it is repeating. So I'm using the same thing now here for x. X is x, but y I'm using pred star length of df.x. Instead of using hard coded 100, what I'm using, I'm calculating length of, if let's say x has 1000, then I want y also to be 1000 values of pred. So to make it better, we have done this, and we have put that graph scatter plot and overlaid mean model. So I got this here. Okay, then anyway, we just reviewed this model. It is not a great model, it is very underfit model. Then we wanted to increase the complexity, so we brought linear regression algorithm from our sklearn.linear model. Then I instantiated to lm, then I separated out my features and target by doing this, and I trained my linear regression algorithm with dot function for my table of information X and Y. Okay, so by this it has understood, trained the model, and calculated for the best fit line some of the coefficients. Okay, I want to go and see what are the, for the best fit line, what is the coefficients. So what is the beta 0 and beta 1? Beta 0 is 0.82 is my beta 0, that is my y intercept. Then because I have y hat equal to beta 0 plus beta 1 x, so only one element has come in my list, and this slope beta 1 is actually minus 0.267. Okay, now I am predicting using my 0, so 0.82, because my x equal to 0 means y hat equal to beta 0, so beta 0 is 0.82, so it is predicting right. Then my intercept is same thing. Okay, and I wanted to check that intercept and all, both of them are same. Okay, using another way. Then I want to predict it for 2, so I passed a 2-dimensional array with 2 there, and it is 0.28. It calculated from my predict function, it calculated 0.28. How it is calculated, I want to see. It has just substituted beta 0 plus beta 1 for x2. So I am doing that only. Lm dot intercept plus, that is beta 0, plus 2 is my x value, star lm dot coefficient underscore is my beta 1. So this is my beta 0 plus 2 beta 1. That is what is actually prediction for 2. Okay, and they are same. Okay, so just to understand what is happening in this algorithm, even if it is 100 XSRs also there, same thing happens. Okay, so then what I'm doing here, I'm actually scatter plot I'm doing as usual, but for my model to be overlaid on top of my scatter plot, x I am giving df.x x column values, but y I am using my lm dot predict function and passing my x values. So for every x value, all 100 x values, 100 y hat values are calculated here. So x and y hat are plotted as a line graph. Okay, then this is what I got it. Okay, so that is how we have done this code. But understand now what is happening. Now I can increase, I can put a polynomial kind of equation. Instead of doing this y hat equal to beta 0 plus beta 1 x, I can increase y hat equal to beta 0 plus beta 1 x plus beta 2 x square. So whatever x value is there, I square it and put it as another column. So in my column now, 2 x's will be there. One is x, another is x square. Maybe I can increase the complexity further. Y hat equal to beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube. Then I'm increasing. In that, my table is having 3 columns, x, x square, x cube. Those are input features, and for that y. Then like that we can keep on increasing and see and do the same things, plot them and see visually, look at it, it's a good model or bad model. But anyway, empirically we have to evaluate, that also we'll do. Okay, so lot of times we have to use the same code. So think now, if I have to do this, play with this a lot, do I need some reusable functions? Can I use my Python functions that we learned, define functions? We can do that, and whatever code that is being again and again run, we can put everything into a simple function and then make a call to that function with right arguments. We can achieve, so we can make it very fast to build more models. That we will do in the next class. Okay, so any questions? Okay, if you don't have any questions, those who have not been able to do it, I'm telling you, this is very simple issue only. Okay, you just type it correctly, it will work for you. Okay, so don't worry and get ready for the day after tomorrow's session. Okay, so bye bye, have a wonderful day, learn, have fun.
Thank you, Madhu. Thank
Yeah, bye bye.
Thanks, Madhu. Bye.
Bye.